So for the next example on the practice exam, we'll look at problem 2.111. And here we have a connection of two cables to a hook. And we also did this problem in chapter 2, but I thought it would be good to go over again. We're given that these geometrical parameters, which are marked in our drawing, are 3 meters. And I'll just kind of draw them in here. And 5 meters. And what we're asked to do is find the angle between the two cables. So I remember when I did this problem on the lecture, I talked about the fact that you always want to leverage the two different definitions that you have of the dot product. Whenever you're asked for the angle between something, always remember that it's likely going to involve the fact that if you have two vectors and you take your dot product, you can either compute it as kind of the traditional linear algebra approach where you multiply the like components and you add, or you can use this geometric approach which involves the cosine of the angle in between. So I'm going to call this the linear algebra approach. And I'm going to call this the geometric approach. So either way, what you're ultimately going to have to do in order to use both of these approaches and ideally be able to solve for cos theta is be able to compute the magnitude of both vectors along with the dot product of both vectors, which means you're going to need this in Cartesian form. And remember, if you have a vector in Cartesian form, you can always compute its magnitude. So really all this boils down to is, for the angle in question, can you actually write an expression in Cartesian form for a vector along the line of action that's separating this angle? So what that means in this case is, can we find an expression to decompose F1 in terms of its x, y, and z components? So F1y, and F1z. And can we do the same thing for F2? Because if we can do this, we clearly see that we're going to be able to compute dot products, and then we're going to be able to compute magnitudes, and we'll be able to do our problem. So if you notice for both of these vectors, both F1 and F2, we're given their magnitude. The first vector F1 has a magnitude of 40, and the second vector F2 has a magnitude of 70. So really, all that we need to do is find an expression for their direction. And if you notice in this case, they're forces that are exerted by a cable. So we know that forces that are exerted by a cable, their direction is really well defined. Their direction is just along the actual cable itself. So really what this boils down to is, can we find the coordinates in space of the three relevant points in this problem, which are point A, point B, and point C. So let's try to do that. Let's try to find the coordinates of point A. Well, if we look at the geometry that we're given, and I'm going to kind of zoom in here, and usually the way that you do this is you actually see if they have a projection of the point into a two-dimensional plane. And in this case, fortunately, they do. So if we notice the projection of point A into the two-dimensional plane, in order to get there, you go out in the positive x direction by 2, and you go in the negative y direction by A. So it has an x component, or an x coordinate, I should say, point A of 2, and a y coordinate of whatever the value of A is, which is 3. But don't forget it's in the negative y direction, right? That's positive y, so this is negative y. So that is kind of the projection of point A into the xy plane. And we're saying it's at point 2 minus 3. And then from there, you go up by 3, and that's going in the direction of positive z. So the coordinate of point A will be 2 minus 3, 3, and that will be in units of meters. In a similar fashion, the location of coordinate B, let's actually see where that is at. And I'm actually going to turn it for a minute just to make sure that I don't do this problem wrong. And it looks to me like that is purely along the y-axis. And I should say, yeah, purely along the y-axis. And in terms of the y-coordinate, that would be a displacement of A in the positive y direction. That means that there's going to be no x displacement. So it's going to be purely along the x-coordinate, rather, will be 0. So I'm actually going to go and write this out. X-coordinate is 0 because it's along the y-axis. Y-coordinate is whatever the value of A is, which we were told is 3 meters. Notice that's in the positive y direction. And in addition, it's sitting in the xy plane. There is no z component, so the z component will be 0. And I'm saying component repeatedly, but just whenever I say component when I'm talking about coordinates, know that I mean the actual coordinate value. So what about point C? Let's take the same approach that we did for point A, and let's actually look at the projection down here in the xy plane. And what we will find is that in order to get to this point in the xy plane, we're going to have to go back in negative x direction by 2 meters. So the x coordinate of point C will be minus 2. Now, what about the y coordinate? How do we get there? Well, we're moving in positive y, but the question is how far do we move in positive y? And if you kind of trace that out, what you see is that is also a units in positive y. So remember that the value for a for us is 3. And then once we go to that point in the xy plane, which is going to be minus 2, 3, we're going to go up by b units. And that up is in positive z. So that would be 5 units up in b. So there we go. Those are the 3 coordinates that we need. So now the next thing we need to do is to write position vectors, right? And if you notice force F2, it's directed along going from point A to point C. So that is the tail is at A and the tip is at C. So the position vector we need to write is the position vector from A to C. And the way that we will do that is we will take the actual tip, which is at C, and subtract away the coordinates of the tail, which is at A. So what I'm going to do here is I'm going to take the x coordinate of C and subtract away the x coordinate of A, and that'll be my x component. So that's multiplied by I hat. I'm going to take the y coordinate of C and subtract away the y coordinate of A. That will be my j hat. And I will take the z component of C and the z component of A, and I'm saying component again, I should say coordinates, and that will be my k hat or z component. So just plugging in the values here, what is the x coordinate of C? It's minus 2. What is the x coordinate of A? It's minus 2 as well. That's my I hat component. What is the y coordinate of C? It's 3. What is my y coordinate of A? It's minus 3. So be careful, and that's the way that you can make mistakes with a lot of these position vector problems is don't forget if you're subtracting a negative, it will eventually become positive. What is the z coordinate of C? It's 5. Minus, what is the z coordinate of A? It's 3. Do your arithmetic there. Minus 2 is just minus 4. Over here, it's going to be 3 minus 3, which is going to be plus 3 or 6. And then in z, it's going to be 5 minus 3, which is just 2. So that vector has units of meters, whatever the units of the coordinates were. So it's going to be minus 4, 6, 2 meters. And always remember with a position vector, you can check and ask yourself, in order to go to A to C, do I have to go in the negative x direction? That would mean I'm going back into the plane. And if you think about it, since A projects out here in positive x and C is back there in negative x, I'm definitely going in the negative x direction. How do I need to move in y? Am I moving in positive y? Well, yeah, definitely in the positive y direction. And what about in z? In the positive direction, I'm going up. That checks out. So that we're going to call that RAC. And then all that we need to do now is get a position vector to describe the direction of this F1 force, which is directed from A to B. Remember, that means that the tail is at A, the tip is at B. So the position vector that I need to write an expression for is RAB. So I'm just going to take, and I'm going to write this in a shorter form. I'm going to take the x coordinate of B, which is 0, and I'm going to subtract away the x coordinate of A, which is 2. I'm going to take the y coordinate of B, which is 3, and I'm going to subtract away the y coordinate of A, which is minus 3. And then I'll take the z coordinate of B, which is 0, and I'll subtract away the z coordinate of A, which is 3. And that will all be in units of meters. Just be careful with your math here. That's going to be minus 2 for the x component. 3 minus a minus 3 will be 6 for the y component. 0 minus 3 will be minus 3 for the z component. And just check and ask yourself to go from A to B. Do I need to go in the negative x direction? Well, yeah, because even though it looks like it's drawn like A is kind of recessed into the paper, remember that its projection is actually out here in positive x. So to go to B, you have to go back. What about in the y direction? Do I move in positive y? Definitely. And what about in z? Do I move down? Yep, I do that as well. So that is my RAB, and that is my RAC. So if I need to here, I can actually take, and it turns out you don't actually have to do this, but I'm just going to show you, since everything that we've talked about so far, you actually seek to write an expression in Cartesian form for the force vectors. But what I'm trying to say is, actually, if you just have these two position vectors, since they lie along the line of action as well, if all you're looking for is the angle between these two, you don't actually have to write an expression for the force vectors. You can just work with the position vectors themselves. So let's actually just do that, just because I think I did this problem in the homework, actually decomposing the force vectors. So let's look at the dot product of RAC and RAB. Remember that kind of taking that linear algebra approach, what we want to do is take the common components and multiply them together. So the x component of RAC is minus 4. The x component of RAB is minus 2. So I'm going to take that product, and then I'm going to add on to that the product of the y components. So that'll just be 6 times 6. And I'm going to add on to that the product of the z components. So that's just going to be 2 times minus 3. So just doing that math there, it's going to be minus 4 times minus 2 is just going to be positive 8, plus 6 times 6 is just 36. 2 times minus 3 is going to be minus 6. So if you do that math there, I'm getting 38. And that would be in units of meters squared, right? Because it's something in meters times something in meters. And then if I have the dot product over here, now I need the magnitude of both of those vectors. So I'm going to take the magnitude of RAC and the magnitude of RAB. Remember, to get the magnitude of the vector, all that you need to do is take the components, square them, and then take the square root of that result. So I'm going to just put that into a calculator real quick. So it's going to be, actually, I'm just going to take and define, just to make sure we didn't make any mistakes. I'll define my vector RAC as minus 4, 6, 2. So the way that you, like if you wanted to compute what the actual magnitude is, you take all the components, you square them, and then you take the square root. So minus 4 squared plus 6 squared plus 2 squared, and take the square root. But when I have that in the software, I can just type the norm function to find the magnitude very easy. So that is 7.4833. And for RAB, I can actually just store that vector, and I will call it minus 2, 6, minus 3. And I will take the norm of RAB, and you should, if you do that, get 7. I'm just going to check my dot product to make sure I didn't do any stupid math issues. I got 38. That's good. So we did it. We can still do arithmetic. I know we can all do arithmetic, but easy to make mistakes, especially later at night. So if you go back to this original expression that relates the dot product in linear algebra form to the dot product in the geometric form, what we can find is that the cosine of the angle between two vectors is just going to be the dot product of the two vectors, which in this case, the two vectors are RAC and RAB, and divide by the magnitudes. So if you do that calculation, hopefully you will get, and I'm going to actually just show one step and get theta here, but I'm going to take those results that I have for the dot product, which was 38. So I'm going to take the inverse cosine of in order to get the angle. In the numerator, I'm going to put 38. And in the denominator, I'm going to put those two magnitudes that I have. And I could just enter the actual values in software if I didn't want to worry about the rounding. But since I'm trying to show you the same thing that you will get, I will enter them manually. The magnitude of one vector was 7. The magnitude of the second vector was 7.4833. Since it's just multiplication, it doesn't matter in which order I do it in. It's commutative, right? So I get there, rounded to 3 sig figs, 43.5 degrees. So hopefully you get that key point. Whenever you're asked to find an angle between two vectors, all that you need is an angle between two axes. You just need an expression for any two vectors that are going along those axes. And if you can express them in Cartesian form, you can take a dot product. If you can express them in Cartesian form, you're able to compute magnitudes. And with those two things, you can basically equate the two definitions of the dot products, as we talked about here at the top, and you can solve for theta in that case. So hopefully that made sense for you. You're definitely going to be seeing one of those on the first exam.